Okay, like I said, any questions before we launch? No?
Can we have a
Okay.
minute to find homework?
Sure. I guess I can remove this tag now. I'm actually videoing. See, I video. You're here.
Yeah. So you can do the video. Oh, for Ethan.
Yeah, I'll video it anyway. We good? Okay, I'm going to actually, we have to finish off a little bit of what we started in the textbook yesterday. There's a graph on page 51, and this is the graph that coincides from on page 5. And it says interpret the following. And interpret means, in your own words, what is happening here, and at the same time, what numbers can we apply to this. So here we are. This is the graph in question. And so it's asking, first of all, interpret this, what's the slope of this line here, and then basically what's happening here. What's the slope of this line from here to the bottom, and what is happening here. And finally, what is the slope of this line, and what is happening here. Okay? Now, this is just an example. This is just somebody taking a ball, throwing it up in the air, goes up, comes back down, and he catches it. That's the moral of this story. So if we just use our, what do you call it? Rise over run, we can calculate that this is, I'll use sticky notes. So the sticky note here is saying that the slope is equal to y2 minus y1, or x2 minus x1. So this is basically 9.8 divided by 0.2. Okay, so this is going to be, okay,
49.
Okay, which is equal to 49. Now, what is the slope of the line? What are the units of the slope of this line? Well, this is meters per second here. Okay, or velocity. Velocity, and this is time. So if this is velocity over time, this is A. Yeah, this is A meters per second squared. Okay? Once it gets to the top, and the slope of the line doesn't change here, so solving for this slope of the line is negative 9.8 minus 9.8 divided by 2.2 minus 0.2, which is negative 19.6 over 2, which comes out to 9.8 meters per second squared. And right there, you should be looking at this thing as, I have seen that person before.
Negative.
Sorry, thank you. Negative 9.8 meters per second squared, and that, of course, is acceleration due to gravity. Okay. Now, what eludes sometimes is, what does this point here represent? Yeah.
Your apex?
This is the apex. Why is it the apex? Yeah. Okay, so you guys are good there. And so on the other side here, on this side here, M is 0. Is that right? No. 2.4. Because that's X. Y is 0. I was right the first time. Okay, now what did I do with my eraser? Oh, there it is.
It should be negative 49 meters per second.
Yeah. Yeah, quite right. So this is goes to 0 minus 9.8 divided by x2 is 2.4 minus 2.2, which is negative 9.8 divided by 0.2, which is negative 49 meters per second squared. Okay? So this is, yes.
So is 9.8 positive in that scenario? So isn't it x2 minus x1? y2 minus y1? So not 0 minus negative.
This is the second point, right? Second point in time. So
Yeah.
this would be x2 should be 2.4. Oh, this should be minus 2. Is that right? No? No, it's 2. Okay. Minus 2.2. Should be 0. Minus 9.8, yeah. So that's going to change it to positive 49. Yeah.
So why is it accelerating in the positive direction when you accelerate now?
In this case, positive. In this case, the positive and negative is talking about the direction.
Yeah,
So he's catching it.
Yeah.
Okay.
Is that the slope from 2.2 to 2.4?
Yeah, from here to here. Okay, he's catching it.
What is it equal? Oh, 49 meters per second squared.
Mm. I think the important thing is that when you look at this graph, you can say, okay, I can see what's happening here. That's about it.
Wait, what is the,
Say again?
like, the video that you did? Was kind of different from what we did.
There?
Well, I've got some scratches up here.
Oh, does that mean anything?
I don't think so. I don't think so.
Which B?
Well,
She's looking at my scratching.
0 to 2, what's the slope from 0.2 to 2.2? What's the point?
Oh, the first one, that's what these stickies are for. This one here is from here
Yeah.
to here. That's the slope there, 49 meters per second squared. Hey, dear. Okay.
Yeah.
This second one, the slope is from here all the way to the bottom here. Okay. And then this last one is going from here to here.
Oh, I see.
Okay?
So
So
what's the point at 1.27?
that is where it's at the top, because that is where the velocity is 0. It's that moment where it just gets, and then it starts to come down the other side. And I think that one, pardon the expression, that one
0.2,
point.
9.8.
I'm sorry, dear?
And just write 0.2 and 9.8.
For what?
The point.
At the top?
1.27.
Well, yeah, 1.2 seconds. Is that 1.2 seconds? I know the first time I looked at this graph myself, I saw it was one continuous line, so I thought it was one continuous motion. Not really. Have to stop and actually see what is the position at this point, or what is the speed at this point.
Yeah.
And
If it was a true graph, it wouldn't have occurred. It'd be like up and then go loop. So,
a graph of what versus what?
Versus time.
oh, I don't know, because velocity slows down. What?
So
Yeah, it is. It's slowing down.
Oh, okay.
It's slowing down to here,
Yeah,
here
okay.
and here.
and then it's going to negative.
Okay.
I know that's why it's hard to reconcile sometimes. Okay, I'm going to do something a little bit different. My suggestion is to grab a piece of loose leaf, because I'm going to write it out.
Little minions.
Any students? What did I do with my stuff? Okay, so this is what I'm going to. This is projectile motion. Okay, so projectile motion actually starts on the next page. How did I do this? How come I've got a mess here? Oh. Projectile motion starts the next page. What I'd like to do is I'd like to forge through a sample calculation, and so that you can have it as a template, and like talk our way through it. And then there are some videos that I'm going to let you guys watch as much as you want, as much as you deem necessary, and then work on 2.2, review 2.2, or whatever you want to get to review 2.2 for the balance of the first block. And then we'll see what happens in the second block, okay? But here we go.
Wait,
Are
what?
we covering page 4?
Mr. Hayden,
Page 4.
watching the news. How's everybody right now?
Nice. No, I'm not going to do that. That's this page here is going to be embedded in what we're doing here. Okay, I'm just trying to, because we're on such a compressed timeline that I have to knock stuff out, knock a bit of discussion out, and to get right to the kernel of the issue. I'm going to be using a bit of color. You can if you want. You don't have to. But I'm going to title this, so this is projectile motion.
I like it.
So this is all in loose.
Are you not using sheets of this
No.
anymore?
Well, we are. It turns out that once we do this, you'll see this and say, oh, okay.
Okay.
Okay, but that's why I say I want to get through the meat of these calculations. And then, and then we can look at, I've got a link there from physics classroom there, which we can use. I've also got a Newton's law, second law apparatus here that we could use if you wanted to. Sure, if you. No, you don't. Just the little thumb through. Maybe what we can do though is maybe let us look at page 6 just just this image up here. What this is doing is, where's my apparatus? Now, ideally speaking, right over the edge, there are two steel balls, and one of them has a hole drilled in it, so it can. So this one's got a hole drilled in it, so this sits on the end, and at the same time this has none, so it sits. It just sits in front of the hammer. When I flip this off, simultaneously, this one will shoot out that way, and this one will drop straight down. Now what you're trying to do is you're trying to listen for impact. Okay. There you go.
Sounds like projectile hit first.
Agreed.
That's in my brain.
No, I think, no, it did hit first.
If it hit first, it was only because there was maybe some fault in how this is set up. Because the reality, assuming a frictionless environment, is that how do I say this? Probably with the picture. This is, if you look at this graph or this image, this is vertical position in meters, and this is horizontal position in meters. So they're actually charting this thing here. Now, what this is trying to represent is only a single ball. What happens if you would shoot a ball like on there? If you're to shoot a ball straight out, okay, its horizontal position, because it's traveling at a constant speed. We're eliminating air friction here. We ignore air friction. If it was at constant speed, because it's at constant speed, its position is going to be uniform in the horizontal plane. Now, if I dropped a ball, that is not true, because it's under the influence of gravity. So what's happening here is this is accelerating. Now, because in this situation, both balls were under the influence of gravity, that means if they're the same mass, well, not even if they're the same mass, because mass has nothing to do with it, but because they're both under the influence of gravity, same gravity is operating on both simultaneously, and they would hit simultaneously, the ground simultaneously. Okay? But the one that's shot also has a horizontal component, and that's what this is trying to show you. If you could, and we can do this, there's a whole ton of YouTube videos that show slow motion photography of this exact thing. Okay? And what you'll see is you'll actually see the ball that's shot travel like this. It arcs and hits the ground at the same time the ball that drops hits the ground. Okay? So when you're talking about projectile motion, the moral of the story of this, that the rationale is this: in order you to determine how far this will go, you have to determine how many seconds it would be in the air if it was a free falling object. Okay? And that is if it's shot from a in a perfectly horizontal. If it's shot upwards, then you have to account for the time up and the time down. Now the time up is going to be equal to the time down. But that time is going to determine how far the thing is going to go. Because if you're going to multiply the time by the vertical component of displacement, or velocity actually, and that will tell you its displacement. Okay? Okay, you just heard me say a whole bunch of words, and probably you're thinking, wow, it's actually really straightforward. But what I wanted to do is I wanted to take you through, give you a template, and then we're going to follow it up by doing at least 2 different examples so that you've got something to go by. But I need my chair. If you guys want to play with this later on, by all means, we'll put it on. Okay. So I'm going to use a hypothetical situation here where, and I also encourage you to always and forever doodle. And I'm going to start off by 2 colors. So this is the angle that we're going to fire something off on. So this is projectile motion. So what this is going to look like is that it's going to start at this angle, but because of gravity, it's going to very soon start to arc. Now, most problems are asking you to solve for this distance here, which we're going to call x. Okay? And so that is going to be this entire. So this, from the data that you're given, this is going to be the horizontal component, the vertical component, but what you're asking to solve is for this entire distance here. Right there. Okay? Okay. So step number 1. Step number 1 is to solve for the vertical velocity component. Okay? Now this velocity here, we are just going to call initial velocity, VO. Okay? What? Which is the angle that it is shot off at, you should consider it a straight line, because we're going to use trigonometry to solve for these 2 guys. But it's only because of the force of gravity acting upon it that it is going to cause it to arc. If there's no gravity, it would just continue to go in that direction forever. Okay?
You could throw a baseball to outer space.
You could throw a baseball to outer space. Well, yeah. Okay? So I'm going to color code this, the vertical velocity component. That's just so that you can relate the words to what I'm solving for here. And we're going to call this V naught y. Okay? So V naught y, yeah, is equal to V naught times sine theta. And so at this point, just as a mental thing, where am I in the process? This gives me the vertical speed. Go bounce it on carpet.
Nobody elementary kids are here.
Yeah, well, that's because that's because they don't have the gym to go to today. Yeah, so they're toast. Okay?
Oh, and the weather's terrible.
Yeah. The second one, number 2, so that's part 1. Part 2 is we want to then solve for the vertical time.
Can you simplify?
Certainly, thank you.
Wait, should we write that formula on our formula sheet?
You know what? On the back side, you probably will have room for it. Okay? Solve for vertical time. And what I mean by that is this is the time that you go up and down total. So this is up and down time. So I am going to just put dots
There,
right next to here.
here,
Oh, sorry. Time. I'm gonna color code it here. This is for vertical time, both up and down. Okay. Now, the beauty of this, of solving for up and down, is that your displacement is equal to 0. Your distance isn't, but your displacement is. So
Are we going to be doing the golf projectile questions?
sure, why not?
oh,
I've got another one before then, though. I'll blow your mind. So the displacement is equal to 0, and this is a thing of beauty because it actually allows us to do the calculation. And so what we're going to do is we're going to substitute this into, we're going to make this equal to 0 for this equation. Better?
Could it be either?
In this case, it's displacement.
But like,
Yeah, as long as it's as long as it's in the same direction.
where are you getting this formula from?
My sheet,
why is it making a
because gravity is in the opposite direction. So this is
Why is there, is that a bracket in front of the negative A?
I was going to bracket the whole thing, but I don't think maybe don't need to.
So is it also valid to write negative half AC squared?
If you like. So what this allows us to do, because this is equal to 0, I can pull one of these over to the other side. Okay? So that's what I'm going to do. I'm going to pull this one over to this side. So, like Ethan suggested, we could rewrite this as VOYT plus, or minus even now, because pulling that outside, 1/2 AT squared is equal to 0. So if I add 1/2 AT squared, thank you. If I add 1/2 AT squared to both sides, that gets rid of it this side and puts it only on this, on the left-hand side. So this is now equal to 1/2 AT squared is equal to,
Time?
say again?
We're solving for time?
Yep, because, and that's the beauty. See, we've only got one t term here. Now I could further change this up by saying t is equal to twice the initial velocity in the y direction divided by acceleration. Okay?
Can we use that equation for everything?
Well, when we're using it in this application, yeah.
So this is the general equation for time is t equals 2.
No, I can't say it's a general one. It
Like
only
this
applies. It applies here.
But like on the test, if I use this equation, will I be safe?
In this application, sure. That's why I'm giving it to you.
Okay. So I
Okay?
don't have to write down all of this 0 equals d on my like formula sheet.
No. Sometimes it'll be more advantageous, though, depending on the question, to use one of these other equations and not go all the way. It just depends on how they're asking it. So third thing you do.
Real
Yeah.
quick. So you make the acceleration negative because it will be negative 9.8 if you didn't want to write 9.8 in? Or why is acceleration negative?
Acceleration is, the reason why acceleration is negative in this case is because the velocity, the initial velocity is in the upward direction, and the gravity is in the opposite direction, it's downward.
Okay, so we switch, if the acceleration is in the opposite direction of velocity, you switch to...
If you, for example, if you drop a ball off of the top of a building,
Yeah.
then there is no upward motion, so you don't have to use the, okay, for example, if you dropped a ball off the top of a building and you were asked to solve for t, for time, and you had acceleration as a negative value, you'll get a negative time. Okay? So when you drop the ball off, if there's no vertical component, upward vertical component, then don't use negative. Use positive, because then you'll get positive numbers. But if it's in the other direction, you throw all that out, because as the projectile is going upward, it is working against gravity, and that's why it is decelerating or getting slower until it reaches a point where its velocity is 0, and then the reverse process happens. It starts to get faster and faster and faster. Okay, so it depends on which way you're going. In this case, because you're shooting it upward, gravity has to be negative. Acceleration of the gravity has to be negative.
In this case, instead of changing it from 9.8 to negative 9.8 meters per second squared, you just change the acceleration? So
Well, acceleration is,
positive.
the acceleration is 9.8. It's acceleration due to gravity. Okay? Yeah. Sorry if I led you astray on that one, but the acceleration at this point is g. Okay?
Is gravity, so you're saying gravity is positive acceleration?
It depends on which direction. It depends on whether you've dropped a ball off and if your initial velocity is in the upward direction, then gravity has to be negative. Okay? If you drop the ball or you throw a ball down, gravity is now positive. Okay? So, step 3 is to solve for the horizontal velocity component. And that's the orange. I'll underline it, the horizontal velocity component. In other words, you're trying to solve for this piece right here, from here to here. Okay? And again, because it's you can use trigonometry, and in this case, you're going to use cosine. So the VOX is equal to initial velocity cos theta. Okay? Pretty straightforward. Now, once you have got this, the horizontal component, this is going to be in meters per second. Okay? It's going to be some value meters per second. To find out how far you went, it's that many meters per second times the time it was in the air. Okay? So, number 4 is to solve for x.
So is our equation pretty much right now a left situation? So we let velocity original y equal v naught times sine theta.
I don't understand what you mean by,
Would
is
we
this a
take what
left?
we solved in step 1 and plug that into our equation in step 2?
This part here, okay, let's just back up. Solving for this, in other words, in order to find out how much time it's in the air, you have to find out how fast it's going up. Okay? So all of this, the first step is just to determine the time. You have to do this first to determine the time. Now it's almost like we split our brain here. We say, okay, now that I know time, I'm going to put that to the side. Then I'm going to solve for this speed here. If you want to use the word speed, I'm going to what's the speed of the projectile this way? Okay. Once I find that, then I could find the speed times the time, how long it's in the air, to solve for the distance that it travels. Okay? Well, when we do it, this, I'm kind of kicking myself for picking this, the example that I'm going to give you, because it's an extreme case. But because you get to the end and you think, well, that's impossible. And you're right, it's impossible because we're not taking into account air resistance. But without air resistance, the physical world would blow your mind. Okay? Very far. Without air resistance. Well, you'll see what I mean. So x is equal to VOX times t. So x, so what we're looking for, is equal to VOX times t. Hey? Oh, zoom in.
Are we allowed to condense this into one equation?
You can do whatever you want.
Is it possible to get one of those
Cards?
sheet cards, please?
Yep. Ask you shall receive. Okay, we good?
Why does x equal the horizontal? Oh, I see.
Yeah, when we do an example, it'll make more sense. I understand that right now this is more or less chicken scratch,
Yeah.
but this is sort of like an overall template that you can apply the strategy for everything, but it doesn't make a lot of sense. It's chicken scratch right now. Let's suppose we have a 22 caliber Swift bullet, and it's fired from a rifle at an angle of 35 degrees. And just FYI, muzzle velocity of a 22 caliber Swift is 1,220 meters per second, which is really fast. What is it? A 38 special is about half that, 600 meters, something like that. I Googled it. And how far will the bullet travel if you disregard friction? So, example. I'll write out the problem. Suppose a 22 cal, and this is called a Swift because they come in different versions, bullet is fired from a rifle at an angle of 35 degrees. A little caveat here, or muzzle velocity. It's 1,220 meters per second. How far will the bullet travel if you disregard friction? Okay? First thing I always do is I always draw diagrams so I know what I'm kind of looking at. I don't need to make it that big. Just need a bit of a doodle. So here we have, I'm going to say this is 35 degrees, and this is 1,220 meters per second. So first thing I'm going to do is I'm going to solve for the vertical speed. So VOY is equal to 1,220 meters per second times sine 35 degrees. I'll spare you the agony. That comes out to 700, pretty much right on the nose, 700 meters per second. It's a little, it's a 700.1 or something, but who cares? So that is solving for this.
What does just VO stand for?
Initial velocity.
And
Y is in the Y direction.
why isn't initial velocity 0? Doesn't everything
Oh, I'm
start
sorry,
at-
this is VO. No, I was right. I'm sorry, say again.
Doesn't everything start at a velocity of 0, like when it's not in motion?
If it start from a standing stop, yes.
Wouldn't have this been starting at a standing
Yep.
stop? So why didn't we put VO as 0? Why did we put it as 1,220 meters?
This when it's coming out of the gun.
Oh, okay. So we're
Yeah, it's not. It's not
barrel.
at its moment of inertia. It's when it's been fired.
Okay.
Okay. Good question, though. So next one. Next up is time. So we want to solve for vertical time. So that's time up and time down. So time up, time down. So I'll just put, yep, thank you, dear. Vertical time. So D, the displacement we said is 0, and this is going to equal, I'm going to plug, I'm not going to, oh shoot, should I or shouldn't I? You know what, I'll put in the raw equation first.
By any chance, does it go 142,718.314 meters?
If what you're asking me is something like 14K, yes.
Add an extra zero.
Oh. I think that's what it goes. It's a big number, I know that. Okay. Oh, do you know what I should do? I'm going to pull that out right away. I'll pull that out right away. That's better. Okay. So, which is equal to 700 meters per second times t minus 1/2 9.8 meters per second squared times t. So I'm going to pull this over to the other side. So
Why isn't it t squared at the end?
T, 1 over t squared, thank you. So I'm going to pull this over, I can't see. So 1/2 9.8 meters per second squared times t squared is equal to 700 meters per second times t. So what I'm going to do here is, because I've got the t term on both sides, I can cancel. So I'm going to cancel the t out of here and cancel one of them here. So now I'm going to simplify it as well in this next step. This is going to be 4.9 meters per second squared times time is equal to 700 meters per second. Oops, that's a t. So t is equal to 700 meters per second divided by 4.9 meters per second squared, and that comes out to 142.9 seconds. 142.9 seconds. That's like about 3 minutes in the air. Holy crap. Friction is our enemy. Okay? So horizontal speed now. 3. Horizontal speed. Yes. Horizontal speed. And I had that as orange on the other one. So I'll maintain my color scheme. VOX is equal to 1220 meters per second times the cos of 35 degrees. This comes out to, believe it or not, 999.4 meters per second. 1,000 meters per second. 1 kilometer per second. Hokey Dinah.
What Mach is that?
I don't know, but it's fast. Distance, therefore, oh, I'm sorry. It should be a 4, not a D. x equals VOX times T, which is equal to 900. Yes.
Can you draw the line coming down like in the drawing that you did?
I'm sorry.
Like in the drawing at the top?
At the top.
Should you draw like the curve that's coming down?
Oh, if you like. If you want to do that, sure. But
That's what we're solving for right now, right?
yeah, so down here is going to be x.
Well, is that the end or that's the whole line?
No, x is where it lands. Because you want to, x really is the distance from here along the ground to here. That's x.
140 feet kilometers later.
Eh?
140 something kilometers later.
It's big, isn't it?
Wait, isn't x displacement because it's straight from that and then distance would have been that whole curve?
Okay. Okay. So
That's right,
displacement. We're looking for, we're not looking for how long the arc is. We're trying to figure out how far did it go now.
But that's displacement, right? Not
It is, but it's also distance too.
how. Because when I was like in physics 11, my physics teacher drilled into me that you gotta like distance is like the whole like actual like thing, and displacement is point A to point B.
No, I understand that. I get that. So if I go with, yeah, fine. If that makes you feel better, then go with that.
It's just a
But yeah, we're not talking about, when we say how far does it go, we're not meaning how far does it travel. We're asking how far does it go when it hits the ground. How far along the ground, okay? Boy, these glasses are really good.
That's how my contacts feel all the time. People always think I'm crying, but it's just my contacts acting.
Yeah. So in other words, the bullet will come down 142 kilometers later.
Question. On this thing, can't you draw the blue like up and down over here so it like looks like a graph? Or would that be wrong to draw it on this side? Like,
Oh, I did it both.
see how I can, because you just do it like over here. But
Yeah, I
can
did it
do
both.
here?
I did it both.
Okay. And that is the same thing?
Yeah, it's the same
Okay.
thing. Now, that was the point when we were playing with adding vectors. You can do it to find the addition of vector. You can go this way. You can bisect the two like that, or you can go this way, or you can go this way. You end up at the same place, so it doesn't matter. That was the point of that exercise, actually. So you're quite right. Why?
He's kind of crying a little.
Why? Because it's for the last thing.
You want that? Is that what you're after?
So what's the exact answer?
It's about 142K.
No, I just want to see if my condensed equation is right.
Yeah, it's above, I don't know, I can't remember. I did it last night. But I looked at that and it's like 142K is fine.
And this is called projectile motion?
Yeah.
Okay. And I can use this for anything to do with
Yeah. There is in our notes. So
Okay,
that's
this
2, that's 4, that's 5, that's 6. On page 7, what I'd like you to do is I'd like you to use the template or the example that we just did, and I want you to solve
For a golf.
for the golf ball. Okay? Do that right now. I'm going to do it off camera, and then we'll come back and we'll compare.
Where is the golf ball located?
This is on page 7.
Page 7?
Yeah.
Am I able to write my test on Monday, last block, in your chemistry class if I just come and sit in?
Say again?
Can I write my chapter 1 test on last block Monday?
Sure.